Today I want to look at power functions. We're going to define what power functions are, and then in particular we're interested in looking at the graphs of power functions. So first of all, what do we mean by power function? Well, any function f of x equals x to the n, where n is an integer and n is greater than 0. Okay, so in other words, I'm talking about the power functions are the guys that are just x to some power, some positive integer power. Alright, now I'm going to show you several of these, and hopefully you can see a trend, and then we'll look at some examples. Okay, so here's some examples of graphs of power functions. I'm starting with f of x equals x, x being the first power here, all the way up through to f of x equals x to the sixth. And really, I think that's enough to establish the pattern that we're looking for here. So, because if you notice, on the top three, I have odd powers, and the bottom three, I have even powers. Okay, and so what do you notice? You notice f of x equals x is a straight line. We know that because it's a linear function. And f of x equals x squared is a parabola. We know that because we know about quadratics. And then after that, f of x equals x cubed, you have kind of this bendy shape going through the origin. But notice that the similarity between that and f of x is that on the left-hand side of the graph, you're below the x-axis, and on the right-hand side of the y-axis, you're above the x-axis, right? So it's going from quadrant 3 to quadrant 1, like that. And notice the same happens with x to the fifth. So it goes from quadrant 3 to quadrant 1. Whereas x to the fourth, you stay in quadrant 2 and then quadrant 1. And so you're staying above the x-axis both times. You end in the same direction. Alright, next to the sixth is the same way. And so what's going to happen here, so if you notice it goes from f of x equals x to x cubed to x to the fifth, you have the same shape, but the higher powers start flattening out the graph around the origin. And the same with the evens. So you have x squared, you have a parabola. X to the fourth, you kind of have a parabola that starts flattening out around the origin. X to the sixth flattens out even more. And you can play with this. If you go to Desmos.com, you can graph x to the seventh, x to the eighth, however high you want. And you already know what the shape's going to look like, but you can convince yourself from there. Alright, now, if you remember dealing with quadratic functions, we had the vertex form of the parabola, which was a times x minus h, quantity squared, plus k. That was the vertex form of the parabola, and the reason that was useful is because if a was positive, it told you which direction your parabola was going to open up. If it was negative, your parabola was going to face downward. And you could also see where your vertex was, hk. Now another way of thinking of that is we could have this formula here. So let g of x equal a times f of x minus h plus k. Now when you do that, it works the same way the vertex form of parabola works. What happens here is a is going to tell you how much to widen, stretch, or condense the graph. It's also going to tell you if it's negative to flip it upside down. The h tells you a horizontal shift. So we always call that the vertex with the parabola, but really what you're doing is you're taking the original parabola and you're moving it h units to the right. It's a horizontal shift. And then the k is a vertical shift. The k tells you how much to move up and down. Alright, so I'm going to show you some examples of this in Desmos and hope it makes sense. Okay, here I am in Desmos, and I'm going to show you how useful this function transformation formula is, because now not only do I know power functions, but I know the graph of a lot of polynomials. So here I'm going to start off with f of x equals x cubed, and what I want to graph here is g of x, which equals 3 times x minus 2 quantity cubed minus 3. Now before our function transformation formula, this seems like a very hard function to graph because it's cubic and we're not exactly sure other than x cubed how to do that. But we now know. So let g of x equal. Alright, so think about it. The 3 is going to tell me what? The 3 is going to condense my graph down. It's going to be thinner than the graph x cubed. I know that the 2 represents a horizontal shift, so it's going to take the original graph and shift it to the right 2 units. And the minus 3 means it's going to shift that down 3 units. So I'm going to take this original green graph, I'm going to shrink it a little bit because of the 3, I'm going to move it to the right 2 units because of the 2, and I'm going to move it down 3 units because of the negative 3, minus 3. So you can see that it's a little thinner than the green line, and if I highlight the point to negative 3, you can see that right there. That's where the origin was in the green, and it shifted down to 2, negative 3 because of our horizontal and vertical shifts. Okay, now if you want to get a better view of that, you can come up here to the wrench, the graph settings, and we can set the x-axis maybe we should go from like -2 to +4. And from there, maybe we can see a little clearer what this graph's looking like close to the origin. So this time let's look at a fourth degree polynomial. Okay, so I know the fourth degree polynomial is going to look like a quadratic a little bit. And this time I want to graph -0.5 x plus 2 to the fourth power plus 1. Before we graph it, let's think about what that's going to do. You have a -0.5. The 0.5 is going to mean I'm going to take this green graph and I'm going to widen it. The negative is going to make that flip upside down. So this graph actually is going to be below the x-axis until we do our shifts. Okay, so now let's think about our shifts. So we have a +2, which means that h is actually, what, -2. This is minus a -2. So that means I'm going to shift to the left 2 units. And then the +1 is going to shift up 1 unit. Alright, so where I was at the origin, I'm now going to be at the point -2, 1. So let's go ahead and mark that just to think. So I started over here at 0, 0. I'm going to end over here at -2, 1. And here's my function. I'll call it k. There it is, my blue graph. Now if I zoom out a little bit, you can see that the blue graph is actually wider than the green. Okay, it's pointed down just like we thought. And it shifted over to the left 2 units and up 1 unit. And there it is. And we know this easily because of our function transformation formula. I have some other examples ready. Let me show you those and hopefully it makes sense. Okay, so now we're going to look at negative power functions, which are very much related to power functions, but in a way are not related at all. Okay, so here what we mean by negative power is f of x equals x to the n, and we want n to be a negative integer, okay, as opposed to a positive integer. Now what does that do to the graph? Well, here you got to remember a negative integer means x to the n underneath a 1, right? 1 over x to the n. So you can't have 0. X can't be 0 because that becomes an undefined value. Now we'll talk more about this when we talk about rational functions. But here are some graphs, alright? So we have f of x to the -1 power. And notice you have 2 pieces here that you don't cross either axis. And they kind of do like that. And then the others look very similar, except the evens stay above the x-axis the entire time, right? Because you can't square something or raise something to the fourth power and get a negative value. All right, but the odds have that symmetry about the origin. All right, and so these are the negative power functions. Now, the reason that we went over that function transformation formula is because they apply for these as well. And so we can graph things quickly just by knowing the basic function and then knowing how to translate it. Let me show you. Alright, so here's my example. First I want to graph f of x equals -2 times x minus 3 quantity cubed plus 1. Okay, that looks like a lot, but actually it's not, because I remember this function, x cubed. I know what that function looks like. Alright, so I'm going to do that in blue, just as kind of as a guide. That's the power function of degree 3, so I know it looks something like this. Okay, now, where does this other stuff come into play? Alright, so the -2 is going to, the negative makes the thing flip upside down, and the 2, since the absolute value of that's greater than 1, is going to compress my graph. Okay, so that would be something kind of like this. Something like that. Alright, now what does the -3 do? The -3 is remember x minus h is a horizontal shift 3 units. So I'm going to take that graph and move it over 3 units, and then the +1 is a vertical shift up 1. So where the origin was right there, the origin is now right here. So this graph looks something like this. Now mine's not to scale, obviously, but that gives you a rough estimate of what's going on with this graph just from one simple technique, one formula, okay? Okay, now for part B, we have g of x equals 2 over x plus 4 quantity squared minus 1. This looks even uglier than the last one, but it's actually not, because I remember this function. 1 over x squared is the same thing as x to the -2 power. So that's a negative power function. It looks something kind of like this. Alright, now what does this other stuff do? It's the same. Remember, it's the same function translation. Okay, so I know the 2 is, since the absolute value of 2 is greater than 1, it's going to compress my graph down a little bit. I know here h is -4, not +4. Remember, it's a x minus h. So that means I have a shift 4 units to the left. All right, so let's get an idea. All right, so first of all, I had something kind of like this, compress my graph a little bit, which is kind of weird with negative powers, but it's not too bad. All right, now I'm going to shift it over to the left 4 units, and the -1 is a vertical shift down. So there's my new origin. All right, so then my graph looks something like this. All right, and you can imagine this is my new axis system, since we kind of have these asymptotes here. So this graph looks something like this. Okay, and if it helps, erase all the stuff you started with. Okay, so I have a graph kind of like that. All right, having a basic understanding of basic functions, we know now linear, quadratic, and power and negative power, really helps us understand what's going on in the algebra. All right, so the better you understand the geometry, the better you understand the algebra, and vice versa. And now we have this fantastic function transformation formula that can help us with a lot of other functions just besides these, and the same principles apply. I hope this makes sense. If you have any questions, please let me know. I'd be glad to help. And thanks for watching.